Hey guys, welcome to this video on the 2020 first mechanics test. So in this test it will be covering the just very short test with just one question on momentum. A person was playing pool and struck a stationary white ball towards a black ball. The white ball is traveling at 2.1 meters per second vertically and hits a stationary black ball. Both balls have a mass of 0.173 kilograms. Alright, so question 1. Calculate the change in momentum of the white ball delivered by the cue. Alright, so we know that the change in momentum is defined as the final momentum of an object minus the initial momentum of an object. We know that the initial momentum of the white ball was 0, and once it was struck by the cue applied a force to the ball, and this force allowed the ball to start moving. Because the ball started moving, it has now gained some momentum. So we know that the initial momentum of the white ball is 0 kilograms per second because it was not moving. So we can say that final momentum minus initial momentum is our change in momentum. We know that our initial momentum equals to 0 kilograms meters per second, and that's because our v was equal to 0 meters per second. So therefore, our change in p is equal to our final momentum. We know that p equals to mv, and therefore p equals to the mass of the white ball, which is 0.173, multiplied by 2.1. Alright, so this actually gets an answer of, just calculate this quick. So 0.173 times 2.1, that should give us an answer of 0.3633 kilograms meters per second. And this is an achieved question here. Alright, question 2. Calculate the final velocity of the white ball. Alright, so as you can see here, when the white ball collides with the black ball, they both split into different directions, and the black ball is moving away at 1.5 meters per second, and we're asked to find the velocity of the white ball. Alright, so we know that the momentum is conserved given that there are no external forces acting on the ball. In this case, in real life, there's actually friction force acting against the table and the white ball. When the white ball rubs the tables, there's an opposite friction force that acts against the motion of the ball. This friction force will cause an external unbalanced force, and therefore momentum will not be conserved. However, for the sake of simplicity for answering these conservation of momentum questions, we will be assuming that there are no friction forces acting on the pool table, and hence there are no external unbalanced forces. This means that we can assume that the initial momentum is equal to the final momentum of the system. The initial momentum of the system, so the system consists of the white ball and the black ball. The initial momentum of the system is just equal to the momentum of the white ball. The reason that the initial momentum is equal to the momentum of the white ball is because the black ball was initially stationary, meaning that only the white ball had a momentum. Because the black ball doesn't have a momentum, and only the white ball has a momentum, therefore the momentum of the system is purely equal to the momentum of the white ball. However, after the balls collide, the white ball and the black ball both have their separate momentums. The white ball has a momentum and the black ball has a momentum. In this case, the momentum of the system is equal to the momentum of each of the individual components that make up the system. So in this case, we have the white ball and the black ball. So the total momentum of the system will be equal to the momentum of the white ball plus the momentum of the black ball. In this case, the white ball and the black ball are moving in opposite directions, so the momentum sum of them will actually be the vector sum of both of these vectors in order to get the total momentum of the system. So we know that because the momentum is conserved, we know that the initial momentum will be equal to the final momentum, which means that the vector addition of the white ball and the black ball will be equal to 2.1 meters per second, the momentum of the white ball initially. So let's get this question started with a quick vector diagram. So in these momentum questions, it's always a good idea to always draw a vector diagram to start out with. So right now we'll start off with our initial momentum. Our initial momentum was just 2.1 meters upwards, but in terms of momentum, it was 0.3633. Alright, so if we draw in momentums of our white ball and our black ball, should look like this. Alright, so there's our momentum diagram. Okay, so you might be wondering how we got this diagram. So how I got this diagram is simply by translating the vectors. As you can see here, we have our initial momentum that's just 2.1 straight, or in terms of momentum, it is 0.3633 kilograms per second in the vertical direction. And if we translate this white vector, if we translate this right here, we didn't change the magnitude and we didn't change the direction of the vector, we simply translated the vector. Same goes for this black ball vector. If we translate it and we don't even change the length and we don't change the magnitude, we're just forming a vector diagram. So we didn't actually change the question or anything, we simply are drawing a vector diagram by translating the vectors. And you'll find that in many of your NCEA exams, you will be required to translate vectors into a vector diagram that you can manipulate and solve. Alright, so what we also know that the angle between the black ball, the direction of the black ball, and the vertical is 30 degrees. And coincidentally, this is the exact angle between the initial momentum and the black ball. This is because the initial momentum of the white ball has been said to be directly vertical, which means that we know that there is a 30-degree angle because in the previous diagram we do know that it was a 30-degree angle between the vertical and the momentum of the black ball. So now we can label our diagram a bit more carefully. So now this is the momentum of our black ball, and this is the final momentum of our black ball, this is the final momentum of our white ball, and we know that this is 30 degrees. Alright, so some of you people might be watching and you might think, oh, this looks like it's 90 degrees. Well, the problem with this assumption is that there's actually no valid proof or any justification that you can say that this angle is 90 degrees, because the question doesn't actually tell you. If you can read the question a bit more carefully, there's actually no justification that that angle was 90 degrees, which means you actually cannot assume that that angle is 90 degrees. Our vector diagram will soon show that angle is actually not 90 degrees. So for this question, you cannot use Pythagoras. So cannot use Pythagoras. This is because we cannot assume any angle is 90 degrees. Alright, so what would we do in this situation? So in this situation, we'll definitely be using the cosine rule because we have an angle and we can find out the momentum of the black ball, and we can find out and we have an angle and two sides, we can find out the last side. So in order to start off, we need to find the momentum of the black ball. That's actually given to us because we know that the velocity of the black ball is 1.5 meters per second. We know that the mass of the black ball is also equal to 0.173 kilograms. So therefore, as P equals to mv, we know that our P must be equal to 1.5 times 0.173. And if we plug this into our calculator, 1.5 times 0.173, that gives us an answer of 0.2595 kilograms meters per second. Alright, so now that we have two sides of the vector diagram, we can use this to find the third side. So this is our momentum of the black ball, this is our final momentum of the black ball. We have our total momentum, so now we can find our momentum of the white ball. So in this case, we'll be using the cosine rule. So if you do not remember the cosine rule from last year, it is c squared equals to a squared plus b squared minus 2ab cos of c. In this case, c refers to the side that's opposite the angle. So in this case, it will be our final momentum of the white ball. The a and the b sides refer to the two sides that surround the angle. The cos c refers to the angle, and therefore we can actually replace the variables in this equation with the variables in our physics problem. So c is actually p, the final momentum of the white ball, and that's equal to our initial momentum squared plus our final momentum of our black ball squared minus 2 times of momentum initial times of final momentum of the black ball cos of angle. So now we have our equation. We can now plug in all our values and rearrange to solve for our final momentum for our white ball. So we have our final momentum for our white ball, that's equal to 0.3633 squared plus 0.2595 squared minus 2 times of 0.2595 times of 0.3633 cos of 30 degrees. Remember to put your calculator onto degrees because we're working with degrees right now, not radians. If we rearrange, we can actually find our PWF equals to, I think it was 0. Let me just put on my calculator. And that is equal to 0.189 0.18983 kilograms meters per second. Now to find our velocity of the white ball, we need to just divide by the mass of the white ball, and that means we can get that P equals to mv, and therefore 0.1983 divided by 0.173, that equals to 1.097 meters per second, and if we round it to 2SF, we'll get 1.1 meters per second. The reason we round to 2SF is because the lowest measurement given in our question was 2SF, and that actually reminds me that we should be rounding this value here to be 2SF as well, my bad. So we have to round this to 0.36 kilograms meters per second, and that's because the lowest significant figures given in the question is 2.1, that's 2SF. Alright, so moving on to the last question of this paper. Question C. At first, the white ball moves without spinning, and after a while it begins to spin. Explain why. So basically at the start, we have to think of it this way. When the person hits the cue ball, at the start, the person only applies a linear force onto the ball. And because the person only applies a linear force from the cue, let me rephrase that. The person applies a linear force onto the center of rotation of the ball, and because it is a linear force onto the center of rotation, there are no external forces, external torques applied. Because there are no external torques, there is going to be no angular acceleration, and hence it will be purely translational motion. So the ball will move with only translational motion, there's no rotation at all. However, as the ball actually rolls on the table, we were discussing earlier that there was actually friction between the pool table and the ball. In our calculations, so when we calculated the momentum and the speed of the white ball, we actually assumed that there were no external torques acting, which means there are no friction forces acting between the pool table and the ball. However, that was only for the sake of simplicity. However, in reality, we do know there is indeed a frictional force acting between the table and the white ball. This frictional force actually provides a torque. The reason it provides a torque is because the friction rubs against the bottom surface of the ball and actually creates an unbalanced external force. This unbalanced external force is acting a certain distance away from the center of rotation. So if I draw a quick diagram here, I hope you guys can visualize this. So we have the ground here and we have the ball. So right here we're going to have a friction force, so FF, and that's going to be pushing the ball this way, an external unbalanced force. External unbalanced. And because the center of rotation of the ball is in the middle, so our distance from the circumference, our force is actually acting an r distance away from the center of rotation. So r distance away from center of rotation. And because we know that torque equals to force times our distance, because there's a distance and there's an external unbalanced force, there's going to be an external unbalanced torque. Because there's an external unbalanced torque, therefore there's going to be causing a rotational angular acceleration, and because there's an angular acceleration, the ball will begin to spin. So basically that's the idea behind this question here. So now all we need to do is put it into words, okay? So when the cue hits the ball, there is only translational motion because the cue hits the ball directly on its center of rotation. This means there is no external unbalanced torque. We'll go to the other page real quick, so we just start down here. There's no external unbalanced torque, hence there is no rotational motion at the start. However, sorry, my writing's very messy, that's not very good. However, as the ball rolls on the ground, well, not the ground, the pool table, to be more specific. Actually, be as specific as you can on the pool table. There is an unbalanced force of friction from the rubbing of the surface of the ball and the table. Surface of the ball and the table. This force acts a distance r from the center of rotation. So COR just stands for center of rotation. I'm running out of space. Center of rotation. Hence, there is an unbalanced torque on the ball. So you can link that torque equals to force times radius. Hence, there will be angular acceleration, and that's proven by torque equals to inertia times angular acceleration. Hence the ball starts spinning. Right, so that's really all you need to cover for that question. So you need to link the ball at start, why it only has translational motion, because the ball hits it directly in the center of rotation, hence no external torques are produced. However, as the ball rolls, there's a friction force, and hence, because of this friction force, it's acting a certain distance away from the center of rotation. This is going to cause the ball to have an external unbalanced torque and cause it to start spinning. So in terms of grading for this question, it's a merit level question. If you can get a full answer and link all the points. To get an achieved, you probably just need to perhaps if you just talk about it, because there was only translational motion at the beginning, because so perhaps if you can get up to here, that might be enough for an achieved. Right, and in regards to the previous question, this is an excellent level question. If you can get up to 1.1 meters per second, to get a merit level grade, let's start with an achieved. So to get an achieved level grade, you can find you can find the final momentum of the black ball that can get you an achieved, or you can use Pythagoras theorem. If you incorrectly use Pythagoras theorem, you can still get an achieved grade because it shows evidence that you still can manipulate the vectors. To get a merit grade, is one minor error with using the cosine rule. So minor error with cosine rule, that gets you a merit grade, okay? And that's the grading for these questions. I hope you enjoyed this video. And if you did enjoy the video, please leave a like down below and leave a comment down below. And I hope to see you all in the next video. Thank you. Bye.